What's up guys, welcome to my first mathematics video in which I will be solving this quite intimidating looking integral. But first, we're going to need a couple pieces of information. We're going to need the fact that inverse tangent of x plus inverse tangent 1 by x is always equal to pi by 2. Secondly, the beta function. The beta function evaluated at u and v is twice the integral from 0 to pi by 2 of sine to the 2u minus 1 times of x times cosine to the 2v minus 1 of x dx. And the beta function has this really cool relationship with the gamma function where it's equal to gamma u times gamma v over gamma u plus v. And lastly, we need one more fact about the gamma function, which is that gamma z times gamma 1 minus z is equal to pi times the cosecant of pi times z. Now, if you don't know any of these facts, I highly encourage you go and watch videos about them to make sure you fully understand those. I currently don't have any other videos right now, but I intend on making videos about these in the future. Alright, now that this is set up, the first step to solving this integral, in my mind at least, is getting rid of this inverse tangent. So we're going to be using this fact here. To take advantage of this fact, we're going to let x be equal to 1 by u, which implies that dx is equal to negative 1 by u squared du. So we're going to get the integral from, as x approaches 0, u approaches infinity, and as x approaches infinity, u will approach 0. So we have the integral from infinity to 0 of 1 plus, and now all of the x's gets replaced by 1 by u's. So we have 1 plus 1 by u, natural log to the 4th power of 1 by u, inverse tangent 1 by u over the root of 1 by u times 1 plus 1 by u squared, and dx here becomes negative 1 by u squared du. I'll bring the negative out front, and we're going to get u squared here, and a better du here. First thing I want to do is switch up these bounds. So we're going to be using the negative sign and flipping those. So we now have the integral from 0 to infinity again. Second thing I'd like to do is take this u square, bring it into this parenthesis, and multiply the whole thing by u over u. Once we simplify some things, we get the integral from 0 to infinity. Take this u into this parenthesis, we get 1 plus u again, natural log to the 4th power of, well, this simplifies quite nicely because the natural log of 1 by u is the same as the natural log of u to the negative 1. With log rules, we can take this negative 1 outside, and everything is raised to the 4th power. So negative 1 to the 4th power is still negative 1. Is positive 1, sorry. So we get the natural log to the 4th power of u. Inverse tangent of 1 by u, we can't do much with that, so we just leave it be. Over u times 1 over root u, so u over root u simplifies simply to root u. Pretty easy to see why. So we have our root u back, and this u squared, when multiplied inside the parenthesis, will yield 1 plus u squared again. So this is obviously still equal to I, and what I'm going to do now is add up both of these versions of I. And you'll notice that in this integral, even though it's with respect to u, we can just do a useless little substitution like u equals x, and we're going to get back to an integral with x. So on the left hand side, we're going to get 2i, and on the right hand side we're going to get a sum of two integrals with the same bounds, so we can combine those into one integral. And you'll notice that everything but the inverse tangent can be factored out. So we have 1 plus x, natural log to the 4th of x. Here we have the two arctangents, so inverse tangent x plus inverse tangent 1 by x. It's an ugly 1 by x. Much better. All of that is over root x times 1 plus x squared dx, obviously. So by the identity I showed earlier, right up here, this is equal to pi by 2. So simplifies quite nicely and we get rid of the arctangent. Now we can factor out this pi by 2 and might as well divide by 2 on both sides. So I is now equal to pi by 4 times the integral from 0 to infinity of 1 plus x natural log to the 4th power of x over root x 1 plus x squared dx. Now this doesn't look much easier, but trust me, it is. What we want to do here is simply let x be equal to the tangent of u, which would also imply that dx is equal to secant squared of u. And now I is going to be pi by 4 times the integral from, as x approaches 0, tangent u approaches 0, as x approaches infinity, tangent u approaches pi by 2, u approaches pi by 2 rather. So we have 1 plus tangent of u, natural log to the 4th power of tangent u. I know this looks disgusting, but trust me. Then we have root tangent u times 1 plus tangent squared u times dx, which becomes secant squared u du. Now you may recognize this as a Pythagorean trigonometric identity. 1 plus tangent squared is equal to secant squared. So this and this cancel out. And we're left with pi by 4 times the integral from 0 to pi by 2 rather of 1 plus the tangent of u natural log to the 4th power of tangent of u. All of that over. I'll write the root of tangent u as tangent to the 1/2 of u for reasons that will be clearer in a second. Now, the last thing I want to do before invoking the beta function is splitting this integral into 2. So pi by 4 all the way factored outside. Oops. We have the integral from 0 to pi by 2. And taking only the 1 now, so natural log to the 4th. And tangent to the 1/2 in the denominator is really just tangent to the negative 1/2. Hopefully you can see that. Times natural log to the 4th power of tangent of u du plus, and now we have the second part, which is tangent u over tangent square root tangent u rather, which is the same thing as earlier when we had x over root x. It's just equal to root x. So we have tangent to the 1/2 u as a natural log to the 4th power tangent u du. And I know this looks even more complicated, but using the beta function, this is going to look much more doable. So let's invoke, let's say we had an integral I of a certain parameter s, which was the integral from 0 to pi by 2 of tangent to the s power of u du, which is close to what we have. But now what I want to do is differentiate 4 times on both sides with respect to s. And using the Leibniz rule for integration, I won't be proving why we can't do that, but you can switch up. Here we would have a d by ds, well, 4 times a d by ds, but we can slip it inside because of the Leibniz rule for integration. And it becomes a partial derivative with respect to s of tangent u to the s power du. To evaluate this partial derivative, it's quite easy. When we're in the s world, tangent u is like a constant, so it's as if you were differentiating like 3 to the s or something. Differentiate it once, you get 3 to the s natural log 3. Differentiate it twice, you get 3 to the s natural log squared 3, and so on and so forth. You just add a log term. So the fourth derivative would be the integral from 0 to pi by 2 of tangent to the s power of u times natural log fourth of u du. And now you can probably see the connection between what I'm doing right now and what we have. You'll notice that this is still the fourth derivative of I of s. And notice that here we have pi by 4 times this integral is just the fourth derivative of I evaluated at s is equal to -1/2. We can take this, replace s with -1/2, and we have our integral. And likewise, this integral on the right is just the fourth derivative of s, but evaluated at s equals 1/2. So we've simplified it a bit, but now the trick is actually figuring out what I of s is. And that's where the beta function comes in handy, because a tangent can be written as sine over cosine. So we have the integral from 0 to pi by 2 of sine to the s power of u times cosine to the negative s power of u du. And this looks quite a bit like the beta function. If I bring it back up, you can see we had an integral with sine and cosine and the parameters. However, we have twice that integral, so we're going to pick up a factor of 1/2 in there. But that's fine. So this is 1/2 the beta function evaluated at. Normally we would have 2u minus 1, but in our case we have s. So this means that u is equal to s plus 1 by 2. And likewise, we would have 2v minus 1 here, but we have negative s. So v is 1 minus s by 2. And this is what I of s evaluates to. Before I go ahead and differentiate, I'm just going to simplify this using the gamma function identity, which I said earlier, which is this one. Beta uv is gamma u gamma v over gamma u plus v. So we have gamma s plus 1 by 2, gamma 1 minus s by 2 over, and gamma u plus v, you'll notice here if we do this on the side, s plus 1 by 2 plus 1 minus s by 2, same denominator, we can add them up. We're going to have an s cancel, and we're going to get 2 by 2, which is just 1, and gamma 1, if you didn't know, is 0 factorial, which is 1. So we don't really need to be dividing by 1. I'm not going to write it. So, and I'm going to make this a bit cleaner while we're at it. So gamma s plus 1 by 2, gamma. And notice that 1 minus s by 2 can be written as 1 minus s plus 1 by 2. If we put this on the same denominator, this is 2 by 2, and we get 1 minus s by 2. And the utility in doing that is that we get gamma z times gamma 1 minus z, which is this identity, which will be pi times the cosecant of pi times z. So finally, I of s is 1/2 times pi times the cosecant of pi by, and I'm going to factor out a 1/2, s plus 1, just s plus 1. So this is what we have for I of s. Now recall that we needed the fourth derivative of I of s. And now I won't be differentiating the cosecant function 4 times, simply because it's kind of long and annoying. But I will input it in a website called Wolfram Alpha if you want to do this on your side and verify. It's very useful. So I'll input this and be right back. So here we have the derivative, the fourth derivative, that is, of this function. As I said, it's quite big. I didn't want to do this by hand. But now we can solve our problem. And before, I would like to simplify one thing, notice that we are evaluating our fourth derivative of I at -1/2 and 1/2. And here, the fourth derivative is actually an even function, because the only odd function in there would be the tangent, but it's always raised to an even power. So overall, we have an even function, and evaluating, that means evaluating it at -1/2 is the same as evaluating it at 1/2. So we really only have pi/4 times twice the fourth derivative of I at 1/2. And this simplifies a bit because, well, 2 times pi/4 is pi/2. So let's get evaluating. We want our original integral I, and we know it's pi/2 times the fourth derivative of I at 1/2. Now this is pi/2 times pi to the 5th over 32 times the secant of pi/4. I'm going to put some parentheses, otherwise it'll get confusing. Tangent to the 4th of pi/4 plus 5 times the secant to the 4th power of pi/4 plus 18 times the tangent squared of pi/4 times the secant squared of pi/4. And I need one more parenthesis. So, multiplying out these first two terms, we get pi to the 6th over 64, which is very weird. You don't see that very often. The secant of pi/4 is 1 by the cosine of pi/4, and the cosine of pi/4 is 1 by √2. So we just invert that, and we get √2. Now the tangent of pi/4 is 1, and even if you raise that to the 4th power, that's still 1, plus 5 times, we just said that the secant of pi/4 is √2. If you raise that to the 4th power, you get 4. So 5 times 4 plus 18 times, again, tangent pi/4 is just 1, and secant squared of pi/4 is 2, because we take square root of 2 squared. So we have 18 times 2. We have √2 over 64 times pi to the 6th times 5 times 4, 20. So we have 21 plus 18 times 2, 36. And this is 57. So we have 57 √2 over 64 times pi to the 6th power. And if that isn't the weirdest result you've ever seen, I don't know what it is. This is the end of the video. I really hope you enjoyed it. If you did, please make sure to like and subscribe, as it would really help me grow. If you have any questions, feel free to leave them in the comment, and likewise if you have integral suggestions. Thank you for watching the video. I'll see you in the next one.